Hello friends, welcome back to my YouTube channel. In part number 19 of my discussion on adsorption, I will solve one numerical, and that numerical is based on multistage counter current adsorption. So this is a continuation of my discussion on stage-wise adsorption. In part number 18, I had discussed the theoretical aspects of multistage counter current adsorption operation, and based on that discussion, today I will solve one numerical. So the numericals will help you to learn how to find out the quantity of adsorbent that can be used in a typical multistage counter current adsorption. So let us begin the discussion. Okay, to begin with, let us look at the numerical statement. A solution of washed raw cane sugar, 48% by weight, is colored by the presence of small quantities of impurities. It is to be decolorized at 80 degrees Celsius by treatment with adsorptive carbon in a contact filtration plant. The data for an equilibrium adsorption isotherm was obtained by adding various amounts of carbon to separate batches of the original solution and observing the equilibrium color reached in each case. The data with the quantity expressed on the basis of the sugar content of the solution is as follows. The data is given in this table. We have different values of kg carbon per kg dry sugar, and we have different values for percentage color removed. So this data is given to us. So basically, in this case, you have a solution of raw cane sugar in water, and the solution is containing 48% by weight of the sugar. And the problem is this solution is containing some colored impurity, and the task is to remove this colored impurity. So it is to be decolorized at 80 degrees Celsius. The operation is to be carried out at 80 degrees Celsius by treatment with adsorptive carbon. The adsorbent that is used is adsorptive carbon. This is the operation. Then an equilibrium data was obtained. Equilibrium data for an equilibrium adsorption isotherm was obtained. How it was done? It was done by adding various quantities of adsorbent to different batches of the original solution, and then the percentage color removed, it was observed. The equilibrium data, in the equilibrium data that is given to us, the quantity is expressed on the basis of sugar content of the solution. So that's why it is kg carbon per kg dry sugar. It is not kg carbon per kg solution. It is kg carbon per kg dry sugar. So in this case, we will have to express capital X and capital Y in a different way. I will shortly tell you how to do that. So you have the equilibrium data that is given to us. Further, the original solution has a color concentration of 20, which is measured on an arbitrary scale, and it is desired to reduce the color to 2.5% of its original value. So the original solution, it has a color concentration of 20, and this color concentration, it is expressed or it is measured on an arbitrary scale. And the objective is to reduce this color concentration to 2.5% of its original value. And for this particular information, with this particular information, we are supposed to convert the given equilibrium data to capital Y, which is nothing but color units per kg dry sugar, and capital X, which is color units per kg carbon. This is the first task that we have to complete. The second task in this case is we are supposed to calculate the necessary carbon dosage per 1000 kg of solution for a two-stage counter current treatment. So the second task that we have to complete is we are supposed to find out the quantity of adsorbent that will be needed per 1000 kg of solution in a two-stage counter current operation, two-stage counter current adsorption operation. That means we know that there are two stages in the counter current operation, and if the operation is carried out in this two stages, what is the amount of carbon, what is the dosage of carbon, what is the dosage of adsorbent that is required if you are going to treat 1000 kg of solution. So this is the numerical statement. Let us move ahead. Now, first of all, let us look at the given data, or let us collect the data that is given to us. So you have an aqueous solution containing a color impurity. So in this case, the mass of the aqueous solution, which we denote by L0, it is mass of the dry sugar in it, plus mass of water in it, plus mass of color impurity in it. And the total mass is 1000 kg. So we are supposed to treat 1000 kg of solution, and the solution will contain dry sugar in it, water in it, and the color impurity in it. The objective is to remove the color impurity by adsorbing it on adsorptive carbon. The objective is to reduce the concentration of the color impurity. We are supposed to reduce the concentration of the color impurity, and how it is to be done? It is to be done by adsorbing it on adsorptive carbon. In this case, only the color impurity is adsorbed. That is the solution which is which contains dry sugar and water in it, sugar solution, it is not adsorbed. LS in this case is instead of in this case LS is not the kg of solution, but it is kg of dry sugar. LS is kg of dry sugar in the aqueous solution. Why so? Because the equilibrium data equilibrium data that is given to us, the quantity is expressed on the basis of sugar content in the solution. So that's why LS is only the mass of the sugar in the solution, or I can say mass of dry sugar, kg of dry sugar in the aqueous solution. So that you need to understand. So in this case, LS is not 1000, but it is kg of sugar in this 1000 kg solution. So sugar content of the solution, it is given to us. Sugar content in the solution is 48%. So that means LS is 0.48 times of L0. L0 is 1000. And 48% of this 1000 kg is the kg of dry sugar, which is nothing but LS. So therefore, LS will be equal to 0.48 into L0. That is 0.48 into 1000. That is 480 kg. So in this case, LS is 480 kg. Then the color concentration, they are saying that color concentration is measured in terms of its intensity. The color intensity is directly proportional to the concentration, and the color intensity is to be reduced. We are supposed to reduce the color intensity to 2.5% of its original value. The original value is 20, which is measured on an arbitrary scale. So as per our notation, this is capital Y0. So capital Y0 is 20, and we are supposed to reduce it to 2.5% of this value. So therefore, final Y in this case is 0.025 times of Y0, which is 2.5% of Y0. So that is equal to 0.025 into 20, which is 0.5. The equilibrium data, it is given. We have different values of kg carbon per kg dry sugar. we will have to convert it to capital X, and for doing this conversion, we will also need the values of percentage color that is removed. So percentage removal of the color is given to us, and we will convert this information to capital Y. So in this case, capital X is expressed as kg of color units. Like, just a minute. So capital X in this case is nothing but color units per kg dry sugar, and capital Y is nothing but color units. No, just a minute. Capital X is color units per kg carbon. Whereas capital Y is color units per kg dry sugar. So the data that is given to us, we are going to convert it to capital X, that is color units per kg carbon, and capital Y, that is color units per kg dry sugar. Let us move ahead. What are the objectives? First objective is to convert the equilibrium data to capital X and capital Y. I have just told you what is capital X and capital Y. So capital Y is color units per kg dry sugar, and capital X is color units per kg carbon. Then the second objective is find the quantity of fresh carbon required in a two-stage countercurrent operation if you are going to treat 1000 kg of the solution. So first we will have to convert the given equilibrium data to capital Y and capital X, and then after that we will be finding the quantity of fresh carbon that will be required in a two-stage countercurrent operation. Let us move ahead. Now, what would be the approach to solve this solution? First, we will change the equilibrium. First, we will change the given equilibrium data to the required form. That is percentage color removed. We are going to convert it to this quantity, color units per kg dry sugar, which is nothing but capital Y, and then kg carbon per kg dry sugar. Using the values given for this quantity and percentage color removed, we are going to convert it to color units per kg carbon, which is nothing but capital X. Once the data is ready with us, the second step would be to plot the equilibrium diagram. So for that, capital X, it will be plotted on the x-axis, and capital Y, it will be plotted on the y-axis. And then after you have the equilibrium diagram ready with you, the next task would be to plot the operating line, on the equilibrium diagram. So we are going to plot a operating line that will cover two stages, because they are saying that the operation, the adsorption operation is to contain two stages. Then once you plot the operating line, you will find the slope of the operating line, and from the slope of the operating line we can easily get the dosage of the adsorbent that will be required. That is the quantity of adsorbent that will be required in a two-stage countercurrent adsorption operation. So approach is simple: change the equilibrium data to the required form, plot the equilibrium diagram, plot the operating line, find the slope of the operating line, and from the slope of the operating line, find the quantity of adsorbent that will be required in the operation. So let us start solving this numerical. Okay, now first we will be changing the equilibrium data to the required form. So we have the equilibrium data. This is the equilibrium data that is given to us. We have different values for kg carbon per kg dry sugar, and then we have different values for percentage color removed. So how are you going to understand this? How are you going to use this data? So for example, if you look at the second column, it suggests that when 0.005 kg carbon per kg dry sugar is added to the solution, 47% removal of the color is achieved. So accordingly, when 0.01 kg carbon per kg dry sugar is added, percentage removal is 70. When 0.015 is added, percentage removal is 83. When 0.02 kg is added, the percentage removal is 19. And when finally 0.03 is added, the percentage removal is 95. Now, in order to get this quantity, color units per kg dry sugar in the solution, so this means that we are talking about color units remaining in the solution per kg dry sugar. So how are you going to get this quantity? It will be obtained by subtracting removed color units from the initial color units. So that's why the equation is color units per kg dry sugar in the solution will be equal to initial color units per kg dry sugar in the solution minus removed color units per kg dry sugar in the solution. So now just look at the first two columns. So here, when 0.05 kg carbon per kg dry sugar is added to the solution, 47% of the color is removed. So that means, how can we use this information in this equation? It will be color units per kg dry sugar is equal to 20, the initial color units per kg dry sugar, minus color units that are removed per kg dry sugar. So 47% of the color units, 47% of the original color units are removed in this step. So therefore, color units per kg dry sugar, it will be 20 minus 0.47 into 20. Therefore, color units per kg dry sugar, it will be 20 minus 9.4. That will give us color units per kg dry sugar as 10.6. So after 47% of the color impurity is removed, 10.6 color units per kg dry sugar are remaining in the solution. And this is nothing but capital Y. So in this way, we convert the information that is given in the second column into Y. So this is nothing but capital Y. So in this way, all other values can be converted. All other percentage removal values can be converted to capital Y. So now we will convert all the values to capital Y. So we have different values for kg carbon per kg dry sugar, and then we have values for percentage removal of the color, and then we are going to get values for color units per kg dry sugar. So first I will enter all the values that are given to us. So these values are given to us. So initially in the solution, we have 20 color units per kg dry sugar. Then when you add 0.05 kg carbon per kg dry sugar, what happens? The color units per kg dry sugar that remain in the solution, it will be 20 minus 0.47 into 20. That is 10.6. I have discussed this. And then we have for when 70% of the color is removed, it will be 20 minus 0.7 into 20, that is 6. Then when 83% of the color is removed, it would be 20 minus 0.83 into 20, that is 3.4. When 90% of the color is removed, it would be 20 minus 0.90 into 20, that is 2. And finally, when 95% of the color it is removed, it would be 20 minus 0.95 into 20, and that is equal to Y. So the values in the last column, these are capital Y values. And now we have obtained capital Y values. Let us move ahead. Now let us look at this first two rows in the table. So if you look over here, the meaning is you are adding, initially there was 0 kg carbon per kg dry sugar. and when you add 0.05 kg carbon per kg dry sugar, the color left in the color units per kg dry sugar left in the solution, they are 10.6. That is, the color reduces from 20 to 10.6 when you are adding 0.005 kg carbon per kg dry sugar. So that means here kg carbon per kg dry sugar, if you increase it from 0 to 0.005 color units per kg dry sugar, this quantity decreases from 20 to 10.6. So that is color units adsorbed per kg dry sugar you can get by subtracting 10.6 from 20. So the difference between the two values will give you color units adsorbed per kg dry sugar. So color units adsorbed per kg dry sugar, the difference is 9.4. That is, when 0.05 kg carbon per kg dry sugar is added to the solution, 9.4 color units, they are removed from the solution. They are removed from the solution. That means they are adsorbed on the surface of the adsorbent, on the surface of the carbon. Let us continue with this. So, after adding 0.05 kg carbon per kg dry sugar, we have obtained this value. Color units adsorbed per kg dry sugar is 9.4. Now, if I take this ratio, which ratio? Color units adsorbed per kg dry sugar, that is this quantity, divided by kg carbon per kg dry sugar. So, if I take this ratio, what is going to happen? Kg dry sugar and kg dry sugar, this will get cancelled out, and you are left with color units adsorbed per kg carbon, and that is nothing but capital X. So, color units adsorbed per kg dry sugar divided by kg carbon per kg dry sugar, it will be equal to 9.4 divided by 0.05. So, this is the these are the color units that are adsorbed, and they are adsorbed on 0.005 kg carbon per kg dry sugar, 0.05 kg carbon per kg dry sugar. So that is color units adsorbed per kg carbon, it will be 1880. So 9.4 divided by 0.05, it is 1880, and that is nothing but capital X. So in this way, you can convert the data in the first column of this table, and in the first column, you can use data in the first column and data in the last column to get capital X. So for the first case, when you are adding 0.05 kg carbon per kg dry sugar, when percentage removal is 47, where the color units per kg dry sugar remaining in the solution is 10.6. So for this, capital X is 1880. What is capital X? Color units adsorbed per kg carbon. So let us move ahead. So now we will convert, we will get all the values of X. So I am preparing this table. You have kg carbon per kg dry sugar. Then we have the values of Y that were obtained previously, color units per kg dry sugar. And now we are going to get the values for capital X, that is color units per kg carbon. So I will first collect the given values. Then we have obtained these values, different values of capital Y. Now we are going to get different values for capital X. So when no carbon is added to the solution, there will be no color unit adsorption of any color units. So X is color units adsorbed per kg carbon. So for this thing, for the second row, when you are adding 0.05 kg carbon per kg dry sugar, color units reduces from 20 to 10.6. So in that case, capital X, that is color units adsorbed per kg carbon, it will be 20 minus 10.6 divided by 0.05. That gives us 1880. I have explained this. In the same way, you can get other x values. So for this, it will be 20 minus 6 divided by 0.01. So that is 1400. Then 20 minus 3.4 divided by 0.015. It would be 1106.67. And then 20 minus 2 divided by 0.02. It would be 900. And finally 20 minus 1 divided by 0.03. It will be 633.33. So in this way, now we have got all the values for x. We had earlier got values for y. So we have successfully converted the given equilibrium data into capital X and capital Y. So finally, I will just collect x and y values. So color units per kg dry sugar in the solution, capital Y. Then color units adsorbed per kg carbon, that is capital X. So we have these values, and that completes our first task. We have converted the given equilibrium data to capital Y and capital X. Now next, we will be plotting the equilibrium diagram. So for that, we will plot capital X on the x-axis, capital Y on the y-axis, and we will get the equilibrium curve. And the diagram will be the equilibrium diagram. We will be plotting the operating line on this equilibrium diagram. So next, we will plot the equilibrium diagram. So plotting the equilibrium diagram. So the scale I have chosen on the x-axis, 1 centimeter is 250. On the y-axis, 1 centimeter is 5. On the x-axis, I am going to plot capital X, and on the y-axis, I will be plotting capital Y. So if I plot the values of x and y that are in equilibrium with each other and that we have just now obtained, so I will be getting a curve which is the equilibrium curve, and this is the equilibrium diagram. Now let us plot the operating line. So end points of the operating line which we will be plotting. One end point is P, which has coordinates of capital X1 and Y0, and the other end point is Q, which has coordinates of capital Xn plus 1, Yn. Now what are these coordinates? I have discussed in the previous video lecture. I have given link to the entire playlist of my lectures on adsorption. You please watch it. I have discussed these notations. I have discussed these coordinates in my previous video lecture. So Y0, it is given to us, it is 20. We know that. So Yn, final Y is also known to us. Yn in this case will be the final Y, which is 0.5. That is 2.5% of 20, 0.5. Then Xn plus 1 is given to us, it is 0. This is the concentration of solute on the fresh adsorbent. And since we are using fresh adsorbent, Xn plus 1 is 0. We are using fresh adsorbent. So you can locate final Y, Yn over here, 0.5. And then you can locate Y0 at Y is equal to 20. Then I will draw a horizontal line. You please remember the operating line which we will be plotting. We will be doing that by trial and error. And for that, based on what is given to us, I have located this point, final Y is equal to 0.5. This is initial Y0, which is 20. And then I have drawn the horizontal line. Now, in this case, the operating line that will be applicable to this operation, it will start at this point. You must have noted that this point is located on the y-axis. This point is located on the y-axis. What is the reason? This point, which has coordinates of Xn plus 1 Yn. Since Xn plus 1 is 0, that is we are using fresh adsorbent, this point is located on the y-axis, and the operating line is going to start at this point, and it will end somewhere on this horizontal line. So we need to remember this while plotting the operating line, because we are going to plot the operating line by trial and error. So what would be the approach? I know that I will have to I know that I have to use two stages. So the construction of the stages will start at this point. At this point, xn plus 1 yn. So the construction involves drawing a horizontal line till you meet the equilibrium curve, and the point where the horizontal line meets the equilibrium curve, once it meets the equilibrium curve, we will have to travel a vertical distance. And to what extent we have to travel vertically, it depends on the location of the operating line. Right now we don't know what is the location of the operating line. We are going to fix it by trial and error. So first, let us say that I draw this operating line, and after drawing it, I am going to check whether this line is the true operating line or not. So for that, what I will do, I will complete this stage. So I have traveled a vertical, I have traveled a horizontal distance. I have reached this point. Now I will travel a vertical distance up to the operating line. So that will complete my first stage. Now for the second stage, I will start at this point. I will travel a horizontal distance. I will reach this point, that is point on the equilibrium curve, and then I will have to travel a vertical distance in order to complete the second stage. But when I do this for this operating line, the intersection of the vertical line, this vertical line and the operating line, it occurs over here. But the requirement is that this intersection, it should occur on the horizontal line through y0. That is, this point should lie on this horizontal line. And since here it is not happening, the operating line that I have drawn over here, it is not the correct operating line. So I will have to change the operating line. So that my objective is to get this intersection on this horizontal line. So for that, I will draw another operating line. I have changed its slope. Again, I will draw those stages. So horizontally, I have traveled up to this point. Now vertically, I will have to travel to this point. So that will complete stage number 1. Then from this point, I will travel a horizontal distance to reach the equilibrium curve, and then I will travel a vertical distance to reach the operating line. Then I will check where the intersection is occurring. Now in this case, the intersection is still not occurring on the horizontal line, that I have drawn through 20. So that means this is not not the true operating line. But even though we have come close to the real operating line, so this point, my objective is this intersection should occur on the horizontal line. Right now I am close to the true operating line, but this is not the true operating line. So I will have to draw another operating line in order to cause this intersection to occur on the horizontal line. So in the next, I will draw a different operating line, that is different in the sense I will change the slope of the operating line. Every time when I draw a new operating line, what actually I am doing, I am changing the slope of the operating line. So now I have drawn this operating line. Now I will complete the first stage. So horizontally I was here. Now vertically I will go to the operating line. Now from here I will travel a horizontal distance to reach the equilibrium curve, and then vertical distance to reach the operating line. And there you are. Now you can see the intersection of the operating line and this vertical line, it is occurring on the horizontal. It is occurring on the horizontal line. That means I have got the true operating line. For this operation, this operating line will be the true operating line which has accommodated two stages in it. So in this way, by trial and error, by changing the slope of the operating line, I have got the operating line that will be applicable for this operation. So I hope you have understood the trial and error approach we need to use for fixing the operating line. Now we have the operating line. We have obtained the correct operating line. Now let us find out the slope, and from the slope of the operating line, we will find out the quantity of adsorbent that will be required in the operation. So for the operating line that we have obtained, which is the true operating line, the slope is given as SS upon LS is equal to capital Y0 minus capital YN divided by capital X1 minus capital Xn plus 1. So in this case, Y0 is known to us, it is 20, Yn is 0.5, it is known to us. X1 we have to read from this point. X1 would be the x coordinate of this point, and you can check the x coordinate of this point is 1410. So in this case, X1 is 1410. Xn plus 1 is 0. The reason is we are using fresh adsorbent. ELS is 480. We had obtained it earlier. Now you just have to use these values. So it would be SS upon 480, that is equal to 20 minus 0.5 divided by 1410 minus 0. That is SS upon 480 will be equal to 19.5 divided by 1410, and that is SS upon 480 is 19.5 divided by 1410, that is SS upon 480 will be equal to 0.014, that is SS will be equal to 480 into 0.014, that is SS will be equal to 6.72 kg, and that is the amount of adsorbent required in a two-stage counter current adsorption operation. So this is the dosage of carbon that is required in this operation. So in this way, we complete the second task as well. So we have completed, we first converted the given data to capital X and capital Y. We plotted that data to get the equilibrium diagram. Then we fixed the operating line by trial and error. Once we got the correct operating line, we found out the slope of the operating line, and then from the slope of the operating line, we obtain the amount of adsorbent that will be required in this operation. So in this way, I complete my discussion for this numerical. I have solved the numerical. I hope you must have understood the steps that I have followed in solving this numerical. If you have any doubts, you can mention them in the comment section. So for right now, I will stop my discussion for this. We have got the solution. Thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. In my next video lecture, I will be discussing how you can apply Freundlich adsorption isotherm to a two-stage counter current adsorption operation. So for now, thank you. Have a nice day, and hope to see you soon in my next video lecture.